Hello again. This is Math 2115 coming to you from the College of DuPage. And the title of this lecture is the Sheffer Stroke and NAND Logic Gates. This is a low stakes assessment. As always, when watching this video, please be an attentive learner, working with pencil and paper in hand. As you know, computers have both hardware and software, and both hardware and software use logic and other elements of discrete math in their design and operation. This LSA involves hardware logic circuits. As you may know, integrated hardware logic circuits are based on transistors. This is the math that you are studying in this course, or at least the logic of that is the math that you're studying in this course. The growth in computing power has followed a remarkable trajectory shown here, and this is known as Moore's Law after Gordon Moore, one of the co-founders of Intel Corporation. And basically, Moore postulated that the number of transistors on microchips will double every 2 years. And you can see that's done that. This might not even look at a doubling, but it's even more remarkable if you realize that this is a semi-log plot. The y-axis is logarithms of those, so it really is even more dramatic than what you're seeing here. This amazing process, however, is approaching a true physics limit because you're approaching quantum distances. Now you, being younger than me, will live long enough to see great breakthroughs. In fact, I might live to see these great breakthroughs involving quantum computing in the near future. Chipsets, such as this one taken from the iPhone 11, have on the order of 10 billion transistors right on this little thing, and actually it's smaller than I made it look in the picture. And these are capable of 1 trillion floating point operations per second. Very powerful stuff. Your cell phone has more computing power than the Apollo vessels that took man to the moon. So there's lots of science, lots of research, and lots of math. So let's go look at some of that underlying math, and we go from this big scale and big numbers to some smaller numbers and smaller scales. This is about a NAND gate, and transistors were invented in Bell Labs in 1947, and a NAND gate for 2 inputs, the inputs here would be A and B, can be fabricated with only 2 transistors. There's the 2 transistors, and this is how you could put such a thing together. But here's what it does. If you take 1 to be a high voltage input and 0 to be a low voltage input, this is what a NAND gate does. And this circuit is sometimes abbreviated looking like this. So this is what a NAND gate looks like with inputs A and B and produces output Y. So here's the output Y. So 1 and 1 gives you a 0 and so on and so forth. This characterizing a 2-input NAND gate. Now, such a truth table should look familiar to you if you take true to be a 1 and false to be a 0. And this is a truth table for an operation that looks like this. It is P, you have the arrow going up into the air, Q, and that is called a Sheffer Stroke. And here's the truth table for it. And you can see this is the same truth table we had previously for the Sheffer Stroke. And the Sheffer Stroke of P and Q, so P and Q, the Sheffer Stroke is the negation of their conjunction. That means that this is logically equivalent, this if and only if this. That's the negation of P and Q. Here's a Venn diagram showing that, and by De Morgan's law, that's equivalent to the disjunction of the negations of the operators, because you just distribute the minus sign, so negation P and Q is negation P or negation Q. You found that in your readings. And some more of the story. The NAND gate connective is most important because it takes only 2 transistors to build it. And as you will prove in this low stakes assessment, all logical connectives we have studied can be built with NAND gates. And because of the logical equivalence spoken of with the Sheffer Stroke, this is the mathematical tool for proving that all logic gates can be built with the Sheffer Stroke. So in a sense, the NAND gate logical operator can be considered the fundamental building block for all hardware logic gates. So here's your assignment. Prove each of the following. Here's a proof, here's a proof, and here's a proof. Now notice this tells us that G, you can build a conjunction just out of Sheffer shifts. You can build a disjunction just out of Sheffer shifts. And you can build an implication just out of Sheffer shifts. And then the last one is a two-parter. You're to determine how to write negation P in terms of P and the Sheffer shift. And then you're to prove that, in fact, you have that logically equivalence. So 5 things to prove, or 4 things to prove, I guess, and 1 thing for a little bit of research. A good project, I think. In closing, remember, time is precious. Each day must count. Do the math. It will make you strong. And also remember to take care of yourself and of each other. We're all in this together. God bless y'all.